In this problem, we are told to titrate a medication to a dose between 50 and 100 micrograms per kilogram per minute. The client weighs 173 pounds. The concentration available is 2,500 milligrams in 250 milliliters. After several titrations, the rate is stabilized at 30 milliliters per hour on the IV pump. The question then is, what is the current dose that the patient is receiving in micrograms per kilogram per minute? Sometimes we think of these problems as working backwards, because many times we start with the dose and we figure out the milliliter per hour rate. However, in this case, we need to take the milliliter per hour rate and go back to the dose. There are two methods to accomplish this, and you can click on the link to go directly to the dimensional analysis approach or directly to the factor number approach. To start with, I'm going to work at converting the weight in pounds to kilograms, because in my original problem, the dose is per kilogram and the question asked is per kilogram. To do that conversion, I take the weight of 173 pounds and divide it by 2.2. Because the weight is above 10 kilograms, I will round my answer to the nearest tenth. So 78.6 kilograms. Now I'm going to use the dimensional analysis approach. I take the 30 milliliters per hour that is set on the infusion pump, and my goal is to convert this to micrograms per kilogram per minute. It's easy for me to convert time, so I know that 1 hour is the same as 60 minutes. I'm able to cancel the label of hours, and I have a label of minutes, which is one of my goals. I can convert the milliliters into milligrams using the fluid that's in the IV bag. In the IV bag, there are 250 milliliters. I'll put that on the bottom of my fraction so that it cancels my other label of milliliters. I'll put the 2,500 milligrams on the top of my fraction. These two numbers have to go together because they're in the same IV bag. However, my goal is to get to microgram. Now that I'm at milligrams, I can use my knowledge of the metric system. 1 milligram goes on the bottom of my fraction, and it is equivalent to 1,000 micrograms. Again, I am closer to my goal. I now have micrograms per minute. The only thing that I need is a per kilogram. Because the kilogram is after the fraction bar, the kilogram must be on the bottom of the fraction. So I will add in this additional label. My one patient weighs 78.6 kilograms, placing the 78.6 kilograms on the bottom of my fraction so that my final label will have micrograms on the top of my fraction, both kilograms and minutes on the bottom of my fraction. At this point, I'm ready to go to my calculator. I'll take 30 times 2,500 times 1,000, divide it by 60, divide by 250, and divide by 78.6. I get my final answer, which is 63 and it continues. Typically a dose is rounded to the nearest tenth, so I'll go with 63.6. My label is now micrograms per kilogram per minute. When I look at the range that is acceptable for this med, it is from 50 to 100. My answer of 63.6 is in that range, which gives me a confirmation that I have done the problem correctly. Next, I'm going to do the problem using the factor method. In the factor method, one way to find the factor number is to use a memorized formula. You'll see the formula show up on your screen in the blue box. To use that formula, I start with the milligrams in the bag, so 2,500. I multiply that by 1,000. I divide by 60. I divide by 250, which is the milliliters in the bag, and I divide by the weight, which in this case is the 78.6. One of the things you'll notice is that the math that I've set up here based on the formula is exactly the math that is in the dimensional analysis. In the dimensional analysis, I multiply the 2,500 times the 1,000 divided by 60 divided by 250 divided by 78.6. The power of the factor method, however, is that you do not have to set up the dimensional analysis. You memorize this information. So I'm going to take this to my calculator. On my calculator, 2,500 times 1,000 divided by 60 divided by 250 divided by 78.6. Typically, a factor number is rounded to the nearest hundredth, so 2 decimal places would give me a factor number of 2.12. The next step in a factor number problem is to use the formula D equals KR. In this problem, we know our K value, we know our rate, and we're trying to calculate the dose. So D equals, using substitution, 2.12 times the rate that's set on our IV pump of 30. Again, I'll go to my calculator and do the math. 2.12 times 30 gives me an answer of 63.6, exactly the same answer that I had calculated by the other method.